Hello everyone, this is Vamshi and my teammates Charan and Vinith are here. Now the paper which we're going to discuss today is finding resume and restart errors in Android applications. Let's start it. Now let's start with the abstract. First let's understand the high level gist of the paper. As the title states, it discusses about the data errors occurred in the Android applications during usage. This paper mainly focuses on constructing a static analysis tool or developing a static analysis tool to find these common resume and restart errors in Android applications. We use smartphone apps daily for almost every purpose, like from navigating to a place to ordering your favorite food from your restaurant. These smartphone applications do generate a lot of data, specifically instance data, just that has to persist across runs. The data which generated between the runs meaning the resume and restart cycles. So let's see an example. So let's assume you're using a application like your personal workout recorder, which basically records your workout timings. If the app is restarted while a workout recording is in progress, the current workout timing information should should not be lost. If this happen, then the purpose of this workout tracking app is lost. So if this instance data which generated by the app is lost or not saved, this causes data loss and it might lead to app crashes and all. Android application has These Android applications has inbuilt APIs to handle this type of instance data. This API is ad hoc, meaning it is created for this particular purpose to save the data by the programmer. Now we can see how important this instance data is for the application. So it's basically important to address these bugs like data loss, failure to resume restart in correct state where it's left, and all. This actually happens due to incorrect handling of instance data and are easily triggered by pressing home or back buttons. To overcome these errors, the authors of this paper developed a tool chain analysis for Android apps. The first one being KRE Finder Static Analysis, KRE Reproducer. The KR meaning kill and restart. We discuss these two analyses in detail in subsequent slides with steps. The above mentioned tools are evaluated on 324 applications and 49 of them are manually analyzed further. This paper states that by using the above mentioned analysis, an approximately of 50 bugs are found in widely used Android applications out there. And now coming to the introduction. The smartphone platform differs fundamentally from the desktop or server platforms. The OS is totally different. The once started desktop programs can never expect to run forever, as the OS will not attempt to kill them when the user switches among the programs, meaning the program going into background. In contrast, in smartphone operating systems, an app runs in a restricted mode once the user switches away from it. Basically, app goes into the background. This is good and has its own pros. Like in restricted mode, it protects the privacy and conserving resources, as the resources are very limited when compared to desktop platforms in Android platforms. And the instance data generated in these runs should be preserved, and these data is called as KR data. The K meaning the kill and R restart. The KR data. The loss of users' work and loss of app or device settings in these cycles is due to incorrect handling of KR data across runs. To overcome these KR errors, the authors of this paper has come up with a static analysis tool which helps in finding the incorrect and inconsistent errors in handling the KR data, the instance data. So to construct the analysis, the tool analysis required surmounting several challenges like identifying the KR data and finding those operations that change, save or restore this KR data, and expressing consistent save, restore and other operations for this KR data in a manner that can be rigorously defined and implemented in a static analysis. So the base KR finder static analysis tools, which we saw in earlier slides, basically produces a report containing the potential bugs which has error location and the path exposing this error. And the other reproducer, which we saw in the earlier slides, takes this report generated by the KRE finder as an input and generates a sequence of inputs to guide the Android app to the endpoint and to find the errors. After applying the static analysis tools developed by the authors stated its contributions in error handling space. Some of them are as follows. The first one, revealing and defining the KR errors, a new class of errors germane to smartphone applications. A definition of KR data, therefore, the data that should be saved and restored across resume and restart cycles. KRE finder, the KR error finder, a static analysis for identifying the KR data and incorrect handling thereof. The KR error reproducer, an input generator to facilitate reproducing errors. By using above mentioned tools, an evaluation on the variety of Android apps, namely 324 of them are evaluated. 49 of them are further analyzed using manual analysis and 291 using automatic analysis. The evaluation has revealed 50 bugs in 37 applications, including 24 bugs in 18 very popular applications in the market. Now let's discuss about Android app lifecycle. Android applications has built-in support for data save and restore and notifying apps of pause and resume operations. In Android apps, the apps are structured around activities. The activities basically, if you can see on the screen, the content in the boxes, these are called activities. So basically, what's an activity? So an activity roughly corresponds to a separate screen in a traditional desktop program with a graphical user interface. These activities are created by extending the activity class. The activities class is an instantiating the subclass. The activity instances follow a life cycle. All these activities instances follow a life cycle, and this life cycle is also known as the Android framework for the particular app. It differs from app to app. These activities move between several states like stopped, paused, and resume, and etc., which we'll see later in the Android framework. Now let's discuss the Android framework and how these activities move in this life cycle. So when the activity is created, an onCreate callback is invoked, as we can see in the figure. The developers can add custom initializing code in these activities. The activity is not yet visible though in this. The activity can move to the started after it is created or stopped. Now the onStart callback is invoked and the activity becomes visible on the screen of the Android app. When the activity transitions to resume, the onResume callback is called or invoked. The activity can become paused when it is partially or fully covered. Example, when you open the menu in an application, the onPause callback is invoked. When the activity becomes stopped, like for example when you get an incoming call or something, the onStop callback is invoked. The activity can be restarted after the phone call completes. This is when the onRestart callback is invoked. When the activity is about to be destroyed and when you want to kill the application, then the onDestroy callback is invoked. After that, the activity is killed, the app is closed. So this life cycle you can see in the right side diagram. So now my teammate Charan will continue and he will discuss the in detail steps involved in developing this KR error finder and KR error reproducer and the main steps involved in it to find the errors while handling this instance data.
The approach mainly consists of two components, the KRE finder and KRE reproducer. The KRE finder is a toolset designed to identify and reproduce restart errors, that is the KR errors, inside an Android application. The KRE reproducer aims to create graphical user interface specific input sequences to trigger a particular method of interest within an app. Suppose, when given an APK file as input, KRE Finder performs a suite of specific static analysis to find potential errors and report KR error path as a summary. The summaries are in a format suitable for KRE reproducer that automatically generates a sequence of directed transitions that land the app in a potential error state. At this point, the app can be paused and resumed so that the errors can be confirmed. The image shown in the slide is the overview of the approach. Uh, when we send an APK file as an input, the KRE finder performs a suite of static analysis, that is the data flow analysis and the control flow analysis, to find potential KR errors and store these KR errors as a summary. The summaries are in a format suitable for KRE reproducer that automatically generates a sequence of directed transitions so that the error can be confirmed. The data flow analysis and the control flow analysis consists of several phases. First one, identify KR data. 2. Find changes to KR data, saves, restore operations and exit. 3. Construct the data flow from KR changes to KR saves and identify potential errors. 4. Construct the control flow from KR changes to exits and identify potential errors. 5. Generate directed transitions for reproducing and verifying the errors. Finding KR data is challenging because this data is application specific. The KR data is a subset of fields in the application defined classes. To identify the KR data, fields need to be mutable and to be modified. That is, field must be changed directly or through an alias in at least one instruction. Fields that are not modified are not considered as potential data. Suppose when application execution does not modify a field, the value of that field is the same across resume or restart cycles. With the KR data fields at hand, we proceed to finding if and how they change. We define data changes as assignment statements where a KR field is written to. However, we ignore assignments in initialization or destruction methods because such assignments are actually initializing or storing variables. In Android, activity is initialized in onCreate method, onStart method, and onRestart method, and destroyed in onDestroy method. Hence, if a field assignment statement appears in these callback methods, we do not identify it as a change statement. Finally, the construction methods of an object or class are also treated similarly. For example, init method and a class method initialize an instance and class respectively. Once we eliminate the changes made in initialization and destruction methods, we are left with the genuine field changes that help us identify KR data. Now, we identify data saves and restores as those call instructions to certain Android API methods that save data to persistent storage and restore data from persistent storage respectively. However, as there are thousands of API methods in the AF, manually enumerating these methods is not feasible. For example, to find data saves, we check whether the method name starts with put when the class name is android.os.bundle. To find data restores, we check whether the method name starts with query when the class name is android.database. The exit of an Android application or activity is different from that of a desktop application, since Android applications are event-driven and does not have a main method. There are three different types of exit statements: onDestroy method, java.language.system.exit call, onStop method, onPause method, which is no longer in use. First, the onDestroy method. This is the most common exit. This can happen either because of the activity is finishing or because the system is temporarily destroying the instant of the activity for cleanup or resource conservation purposes. Second, java.language.system.exit call. This call terminates the current running Java virtual machine. Third, the onStop method. This method is called when the activity is no longer visible to the user because another activity is resuming, hence forcing the current foreground activity into the background. The fourth one is the onPause method, which is no longer used since exiting directly after onPause method is rare. KR data saves and restores are critical as their absence can lead to KR errors. Missing KR saves or KR restores or missing both leads to KR errors. We divide KR error reports into four loss types. Type 1. A KR field has only one save operation that is placed in methods that are not guaranteed to be called by the AF. Hence, the KR field value might be lost. This is where a KR field is modified while the app is running, and its save operation is placed in onDestroy method. If the app is killed after onStop, we have an exit without save, hence the KR field is lost. Type 2. A KR field has at least one save operation, but there exists a path from the data chain instruction to an activity or app exit, and the path doesn't contain any save operation for the data. Hence, the KR data value might be lost. Where a KR field is modified while the app is running and its save operation is placed in onPause method which is invoked, but due to branch condition being true, control flow will follow the then branch. Hence, again we have an exit without save and KR data is lost. We discover type 2 errors using a two-stage analysis. In the first stage, we use a must forward analysis to find those changes to KR fields that flow into saves. The second stage is a must backward analysis that has to discard the saves placed in methods that are not guaranteed to be called. Type 3. A KR field has no save and restore operations. If there exists a statement that changes the field, the changed value will be lost, but a KR error does not necessarily occur. Example: when a post restart application state is not data or control dependent upon this field, there is no data loss from the change to either a save or a restore method. Type 4. This loss occurs when a KR field does not have a save operation, but has a restore operation. If the KR field is restored and then changed, we infer that it should have been saved. Where a KR field is restored after restart in the onRestore method, but KR field is never saved prior to restart. The restart is performed in a method guaranteed to be called upon app application start, and there exists data flow from the restore to a change. After finding the potential losses, we produce error summaries. The error type, the KR field name, and location, that is, the method and change instructions for that field, and also a summary of the control flow path that leads to error. After getting these summaries, we can move to reproducing and confirming the errors. For this, we use a suite of static analysis to construct directed transitions, that is, sequences of graphical user interface events and method callbacks that must be invoked to drive the execution to the error location. Once the app is in error location, we can go through pause and resume cycles to confirm the errors. We will now briefly discuss our static analysis implementation as well as the implementations associated with error reproduction and error report verification. Static analysis with KRE Finder. KRE Finder is based on Floydroid, which is an open source static analysis tool for Android applications. The analysis is context flow and object sensitive. Floodroid's main goal is static taint analysis, that is, determining whether a tainted source reaches a security sensitive sink. Floodroids was extended in two directions. The first one is fine gain flow tracking, second one is scalability. First, Floodroids only supports marking methods as sinks and sources, but not arbitrary instructions. This hinders the process of finding KR errors, since finding such errors requires the ability to trace data flow between instructions. We thus extended Floydroids to be able to trace flow between arbitrary instructions. Second, Floydroids requires large amounts of memory for large applications, while scalability can be improved by setting certain command line arguments. Increasing scalability will reduce precision. Verifying and reproducing KR errors. After KRE Finder completes producing a set of potential bug reports, our KRE reproducer helps reproduce and verify the errors. KRE reproducer uses a combination of new and extended tools consisting of mainly two steps. First, creating in a directed transition to the error point on legal app execution paths. Second, forcing the app to exit to mimic an actual scenario, either pause and resume or kill and restart and observe the results. The directed transitions generated by the KRE reproducer will guide app execution to error points, while generating inputs to direct execution to a certain program point is of course undecidable in the general case. The graphical user interface oriented event-based nature and shallow stack of Android applications make it easier in practice to reach a certain point in a certain method. Generating the directed transition path. Based on KRE finder's output, we identify the methods we are interested in. Next, KRE reproducer uses Redexer to generate a sequence of events starting from the application's home screen that will provide a directed transitions to the methods specified, creating sets of valid view event pair. KRE reproducer maps the events with required view elements. To do this, KRE reproducer uses Gator, which conducts static reference analysis to create one-to-one mapping from view elements to their associated callbacks. Now we have a sequence of callbacks ready to be fired. Once the app is in potential error state, we need to drive the app down an exit path, which varies depending on the desired restart level. We have now triggered restarts at three different levels. First one, pausing the app by popping up a dialog teamed activity which invokes a onPause method. Second, stopping the app by pressing the home button which invokes onStop method. 3. Kill the app by pressing the back button which invokes onDestroy method. After the app exits, we restart it. Upon restart, one of the error categories will materialize or the app might even crash outright. To get a hold of the error details, we track individual application fields, that is the KR data that the static analysis has identified as potentially being lost. To conclude, we have constructed an end-to-end system that, given an Android application as input, will automate KR error discovery, location, and reproduction. Now, my friend Savinith will continue with the evaluation part.
Coming to the evaluation, we have evaluated our approach along two main dimensions. One is effectiveness and another one is efficiency. We have got few questions on both effectiveness and efficiency. They are: in effectiveness, can the approach run on popular off-the-shelf apps? And is the approach effective at finding potential bugs? Efficiency, does the analysis complete in a reasonable amount of time? And is the process burdensome for users? Let's see the methodology. First, now we downloaded and examined 334 apps from Google Play, Apps APK and Google Code.
In particular, the 334 applications cover different categories such as email, SMS, games, etc. and have variety in terms of size from 3 KB to 26 MB and have variety in terms of popularity. From these 334 apps, we have constructed two datasets of 324 apps and 37 apps respectively, as shown in the table 6. Of the 334 apps, 324 could be successfully analyzed with Floodroids. We named this dataset as SA324. Among these 324 apps, our static analysis reported potential errors in 114. Next, we attempted to decompile the 324 apps using the DARE and Dex2jar decompilers. From 324 apps, only 109 could be decompiled successfully. Out of the 109 apps that could be decompiled, the static analysis reported potential errors in 49. With the decompiled source code for the 49 apps at hand, we manually analyze the source code to discern false positives from true positives. We found that 37 apps had true positives. These constitute the TP37 dataset. Our evaluation henceforth proceeds on the SA324 and TP37 datasets. Coming to the effectiveness, SA324, the app characteristics and overall results for the 324 apps are presented as shown in the below table 7. The largest app in the dataset, Facebook, was about 23 MB in size, while the median app size was 168 KB. The analysis found potential errors in 114 out of 324 apps, hence the average zero point 0.8 reports for the entire dataset. Across those 114 apps with the potential errors, there were 2.3 error reports per app on average. This table 8 shows app characteristics and analysis result for the apps in TP37. We assign the name, version, size, popularity, static analysis time, the number of true positives, and the number of false positives for every app. The true positives were confirmed using the error reproduction process, while the number of false positives can be further reduced by improving the precision of the static analysis. We found the process of triaging to be quite efficient. Hence, even for apps with a high positive rate, we believe that the error production burden is acceptable. In table 9, we provide a detailed description of 49 bugs we reproduced. As we can see, the error manifestations vary depends on the app. Many of the errors were present in table 9 can be found in the apps reviews on Google Play and Google Code. For example, brightness profiles. When the application window disappears, brightness returns to previous level. As soon as you exit to home screen, brightness level jumps back to the phone's minimum level. The lowest brightness level doesn't stay dim, even with or without auto bright off. Randomly sets back to 100% and auto brightness after using camera. Error manifestation categories. Based on the reproduced errors, we now categorize KR according to their manifestations. They are losing GUI state, losing users progress, losing device settings. Let us see losing GUI state. While Android supports saving GUI state across restarts via the default implementation of on-save instant state, the GUI state loss can still occur for two main reasons. The first one is on-save instant state method is not invoked or the app has a custom GUI that is not managed by the AF. Coming to losing users progress. In many cases, KR error leads to losing users work, play or workout data. And the last one is losing device settings. Many KR error leads to device setting being lost. The phone's flashlight seeing is lost in semantic Norton snap. The speaker phone setting is lost in speaker proximity. The camera setting is lost in Motorola camera. The Bluetooth setting are lost in BTHF, PowerSafe and Fox5. False positives. As with any static analysis, our approach is prone to scalability issues and false positives. We have identified four main sources of false positives. One is many false positives are potential loss type 3. The second one is source is flow imprecision. The third one is an app may offer GUI option for saving data. And the last one is imprecision in suits alias analysis. Efficiency. Let us see static analysis efficiency. SA324 running the static analysis on the entire dataset took 6 hours. The time column in table 7 that I have shown before shows running time statistics. The mean analysis time is 61 seconds while the median is 22 seconds, which shows that our analysis is practical. TP37 Table 8's time column shows the individual running time for the 37 apps with true positives. While time ranges from 8 to 1569 seconds, the analysis typically completes in less than 5 minutes. The next one is input generation efficiency. The input generation stage took less than a minute for the examined apps. We omit individually number for brevity. Error report triaging. While we didn't precisely measure the time it took to triage the error reports in the manually analyzed apps, the first author as well as the second author were consistently able to triage each error report as follows. Ruling out a report as a false positive takes less than 5 minutes. Understanding and reproducing a bug takes about 10 to 15 minutes. Of course, in case of multiple error reports, the cost for triaging subsequent reports is lower due to initially learning curve. Note that the apps were unfamiliar to triages, so we expect the time to future reduce when developers run our analysis on apps they are familiar with. Related works, resume and restart errors. Let's go through this. An app testing tool named Quantum uses a library of interaction features to test apps by constructing parsimonious test cases from GUI model and interaction features. Quantum compares GUI state before and after features are exercised. Their features include screen rotation, killing and restarting the app, pausing and resuming the app, and pressing the back button. Quantum and our approach differs most fundamentally in the traditional testing versus static analysis way. The first point is we use a sound static analysis whereas quantum is dynamic. By comparing GUI state, they find only those manifestations of KR errors that are reflected in the GUI, whereas our approach can find those and more subtle losses that might not be visible in the GUI. Our approach is fully automatic, whereas Quantum requires a GUI model to be manually constructed and manually validated by the user. We focus exclusively on resume and restart errors, whereas their focus is on generating parsimonious testing suites from a library of user interaction features. We focus on batch analyzing dozens or hundreds of apps without requiring access to app source code. Our directed transition generator produces event sequences rather than test cases as Quantum does, with the goal of hitting a certain program point. Finding smartphone specific bugs. App Doctor tries to find bugs by injecting various events into app's execution. One such event is rotate. They mention the problem of apps having to handle restart at any moment, but their approach does not focus on this problem as we do, and instead their goal is to find bugs by rapid firing of events. They found two bugs where rapid event firing catches the app in an inconsistent state, but the bugs are due to rapid event interleaving rather than the state loss upon restart. Most of the smartphone specific analysis and verification work so far has focused on other kinds of bugs. Our work differs in two key regards. First, we focus on a new class of bugs, KR errors. Second, we use static analysis which is sound but incomplete, whereas dynamic analysis unsound but complete. Finding persistency bugs in traditional application. Prior efforts on persistent data consistency have looked at file system or database errors. Checking to find errors in a file system code use checkers based on declarative specifications to check the integrity of and repair file systems, impact of disk data corruption on database integrity. These techniques, though, are not directly applicable in the context of KR data handling on Android due to the significant difference in domain applications and consistency properties checked by their and our approaches. Directed testing. While automated testing approaches for Android abound, most of them do not aim to hit a particular state or program point. Collider uses symbolic execution to reach a target instructions. Hence, it can generate a precise path condition for reaching the target. while in Collider, UI models were built manually. They could be constructed automatically using third-party tools. Collider requires access to the application source code. It is unclear how well the symbolic execution scales to a very large app. Our directed transition method is less precise. It could potentially fail for complicated path conditions, though we have not seen such failures on our data set. In general, we aim at a different design point, a scalable approach that can be applied efficiently to large popular apps from Google Play via a fully automatic tool chain and without requiring the source code. Coming to the conclusions and future work, we constructed novel static analysis and tool KRE Finder that combines data and control flow analysis to automatically find potential KR errors in Android apps. The error reports are passed to another tool. We constructed KRE Reproducer, which generates input sequences to help users verify the report. We believe that our technique finding which data survives a restart opens a more general research direction, exploring the trade-off between oversaving and undersaving. With our technique, app developers users know exactly what data survives a restart and whether a restart will lose state or can clean up the state. Thank you. Any queries?